Hi, this is Shootstype, and in this video I'm going to show you how to use the template script generated by Protosc. So after installing, go to your command window and type Protosc template. Then give a file name and run it. So you can see a new file with your file name is then created, and it's already filled up with an analysis. So let's go through what's inside here. So the first thing that you should change when you're looking at the script is where your stuff is, where your files are. So mine are actually here, and this is for grabbing two categories from one directory. But you might have your images in different directories, so then simply copy paste this line, set it to the second directory, and make sure that it's in the second location of the variable imdir. Then, just like in the app, indicate what should be in your file name. Now for each category, you add a string in this cell. So for two categories, you have two inputs. So the first category needs to have an underscore O point. If I want to use a more complex term, let's say, well, they have to have this, but they also have to have this. Simply add it after adding an asterisk. So term 1, asterisk, term 2. If you want more, another asterisk, term 3. If you have more categories, simply provide more inputs to this variable. The may not include allows you to add exclusion criteria. It works the same way, but I don't have any exclusion criteria right now. Let's say that you do. Let's say that you want to remove this from category 1 and this from category 2. Enter it as such. For now, we'll just leave it an empty variable. The next is creating a file list. So based on the inputs that you gave here, you have the imdir, the locations, what should be included and what should be excluded. A file list is created. So let's see how that looks like, because I already ran this. So this is my file list. It's a cell struct. So let's look at the files in the first category. So it registers the name, the full name, what needs to be included and what needs to be excluded. So let's look at the first example. So this is for the first image file. So the name is actually the file name, and the full name is the name including its path. This is the one that's really important for loading the files later. And this is all just for registration so that you can find it later, what you did. Now, at the end of the script, two files will be created, which I'll show you more about. And one is a methods file and one is a results file. So here you can give the file names for that. We'll get into that later. This section is for you to choose what feature types to include. So you can pick one or you can pick many. I ran the analysis such as this. So this is for Fourier features. Phases are excluded and the Fourier features are downsampled. This is for Fourier features, magnitudes and phases together. There's no downsampling on the spectrum, but the images are downsampled beforehand. This is for phases only as well. Here, no downsampling of the phases directly, but downsampling of the images. And the downsampling in these two is to keep the number of features relatively low, because you get a Fourier magnitude combination for each pixel. This is for hog features. This is for color distributions. And this is for pixel intensities. So setting 1 to one of these will include it in the analysis. So the main difference with the app is that you can choose much more things here. So these are the most relevant settings of Protosc. So it's in a struct. It looks like this. It's actually quite big. And these are the ones that you might be interested in. That's at least what I thought. So there's information on each of them behind it. Just let's walk through it anyways. So when you have RGB images, but you are using a particular monitor, you might want to convert the RGB values to luminance values. So that's what this is for. So standard, it's set to 1, so it really doesn't do anything. But by changing these values, well, you can convert them to luminance values, which might be more relevant, especially if you're doing a behavioral-based analysis. So if the labels for the images are based on behavioral choices. Images are all standard converted to a particular size. So this is the size that they are standard converted to, except for when we're doing analysis based on phases and magnitudes, or pixels. Then they are set to an other size, which is this, which is relatively small. A boolean to indicate if you want to make the images grayscale. A boolean if you want to indicate if you want to convert the RGB values, and then the function to convert the RGB values with. So this is to convert them to CLAB. These two are specifically for the Fourier features, and it indicates how to segment the Fourier space. So here it's segmented in 16 orientations and 24 spatial frequencies, which is the default. This is for segmenting images when you're doing an Hague analysis. So the images now standard are segmented in areas of 10 by 10 non-overlapping pixels. So that area of 10 by 10 pixels, that's where we check the histograms of oriented gradients using X orientation bins, and in this case that's 9. For the distribution steps, that's for the color distributions per color channel. The probability density function is calculated and binned in 25 bins by default, and that's how you get the color distribution values. So when you use 3 channels RGB, you get 75 values reflecting the distributions of the color values in the images. This is to indicate if you want to grab a specific channel from the image. So let's say you're using RGB images and you only want to do the analysis on the R channel, on the red channel, you can indicate a 1 here. If you only want to do it on the green channel, 2, only on the blue channel, 3, or let's say you want to do it on the green channel and the blue channel, 2 and 3. So just leave it empty if you if you want to use all the channels of your image. This is for if you want to use the Viola-Jones algorithm. So set it to 1 if you want to extract faces from the images. And the way we use it, we extract a face and then we add an extra area, a little extra area, and that area is defined as a percentage, and that's here. So face add percentage. Linking features is mostly relevant for when related to color. So should we treat, for example, with the pixels, for a particular pixel in a particular location, should we treat the RGB values as a single feature or as separate features? If they're linked, they're treated as a single feature. If this is set to 0, they're treated as separate features. For in an exclusion in the during feature selection. This isn't actually that relevant right now. It's the ranking function we use to rank the features before making a filter model. But we have only one function for this implemented. But in later versions we might add more, so that's why it's here. Same with the classifier option. So this is the main classifier that's used for decoding the function of it. When we add more, you have more choices here. How many folds should we use for cross-validation? Standard set to 10. So this is the sampling percentage, and this is relevant to the wrapper. So the wrapper does lots of training and testing models on the trained data before it is cross-validated on the holdout data. So within that training data, that's split up in 50-50. 50% is used for training, the other 50% is used for validation. If you set this to 70, then 70% is used for training, 30% is used for validation. So that's for selecting features. You can give particular folding indices, which is useful if you want to rerun the analysis using the same types of folding indices as you used before. This can be used to force a particular fraction of features into a model, into the filter model. So if you set it to 0.1, the top 10% of the features will be forced inside of the filter model. This is to make correlated clusters. So if you set this to 1, features that are highly correlated are grouped together and treated as a single feature during the analyses. So at this point, you don't really need to do anything anymore. But let me show you what it does anyways. So from must include, we create label names, which is something that is stored later for you, basically. So when we load the images based on the file list, the settings, and the label names, we get the variable stims from which we can extract features. So let me show you how that looks. Again, it's a cell. So this is the first category, 331 images, and this is the first image. And here we see the image itself is an im, so if I want to see that, I can do this. What is it? Stims. There it is. That's the first image in the first category. That image got a label of 1, a label name of _o point, an ID of 1, which is just because it's the first image. This was the file name. This is the full file name. This was our settings for inclusion, our settings for exclusion, the size of the image. If we extracted a face, no. And face percentage, well, that's just registered. Okay, so now that we have all the images, all the stims grabbed together, all the images grabbed together, I'm gonna pre-allocate some stuff here. We're gonna put the features in here and the reference frames, which tells us which helps us find where the feature where the features came from in here. So this is just a big if statement to see which features you wanted. So in this case, only get Fourier features was set to 1. So it's going to run the function to get the Fourier features based on the stims and the settings. And it's going to output Fourier features, which is which looks like this. Again, a cell. Well, It's not very useful. Yeah, let me just do it like this. So 331 examples, 338 features for 3 color channels. Now that information is going to be put into this function here, together with the settings, to create a matrix called all data, which contains all the examples. So 331 plus 282. You notice maybe that there's one more column, and that's because the first column is the label of the images. So lots of ones and then lots of twos. This one creates the reference map that we'll use for visualization. Now notice that when you run multiple, like if you do multiple at once, so for instance here you do Fourier with Hawk features, then they are simply combined in all data, and the reference map is also combined. This runs the actual feature selection. Like I said, I've already done it, so here are the results. This is the normalized chi-square. So in the reference frame of the downsampled Fourier space. So you can see all these wedges, that's the downsampling. And we use the Fourier space just as is, which means that along this axis reflects contrast energy in horizontal horizontal edges. And the horizontal axis actually reflects contrast energy in vertical edges. And here it's diagonal. So we see that there's quite some differences around here, so that's what you would expect as mainly the relevant features, but we'll see that that's not the case. So this is just to give you an overview of, with a simple chi-square test, where would we expect, how are the images different, where would we expect the relevant features to be. Here we show the percentage cumulative sum over the number of features. So what this does is it takes the feature with the highest chi-square and puts it on position 1. Then it takes the sum of the feature with the highest chi-square and the second highest chi-square, convert it to percentage, put it on 2, etc., etc. So here you see a nice curve. It's relatively steep, meaning that the chi-squares are not equally distributed at all, and there's a few places with lots of with high chi-squares and a lot of features with relatively low chi-squares. So if they all had roughly the same chi-square, you would see it this line along the diagonal. Here is the cross-validation accuracy as fraction correct, with the black dashed line being the median of chance distribution and the red being the 95 percentile of the chance distribution. And you see that nothing really surpasses these 95 percentile, which is interesting because, well, hold on, let me tell you some more about this. So there's multiple bars, one for each approach. So this is for the filter approach that we use, for the wrapper approach that we use, which the random approach and the pseudo-random approach. This is as for comparison if you do not do any feature selection at all. These are the relevant features, the ones that are deemed significant by Protosc. which is interesting because here we don't see any clearly significant performance for any of the individual methods, but during each fold, each method can grab a different group of features. So this is to look at how well can a particular method decode the data, and this indicates if a particular feature or group of features is consistently associated with above chance performance. And we see that they are. So let's look at which features they are actually. So the struct out is created, and it has a lot of stuff in it. I'll make another video on that. Let's for now just look at features of relevance. So in main findings, there's a bit of a summary. So let's just double check if any of the methods were significant. So we see the filter selection mean accuracy, 60% with probability of 0.1. Well, not significant, of course. Similar for the wrapper, similar for random, and similar for the pseudo-random selection. But we do find 19 significant features, which is interesting. So here we see the significant features, and we see that the highest scoring one is 283. So we made this I made this function to help you find features in the space, in the reference space. Find feature, okay, and then we add the out struct, and I want to know where 283 is. Ah, there it is. So it's along the diagonal. The Fourier space has low spatial frequencies in its center and high spatial frequencies on the outside. So it's relatively high spatial frequency. So if you see relatively high spatial frequencies differentiate between the two classes of images. Okay, that's it for now.